Okay, I think get this out of the way though. Okay, and we're recording. I think we're ready. Okay, so welcome to day 2 of Crash Course Propulsion. So here's the agenda for today. We're going to be talking about our oxidizer called Nitrox. We're going to talk about CEA, which is a online software tool we use. Myron is going to talk to us about the Oxidizer Tank, and we're going to talk about the feed system. So one of the things we wanted to start with today that we added in based on how last session went was we realized that in rocketry there are a lot of terms that we use all the time and we're just so used to using them it's hard to get away from them. So we wanted to define them ahead of time just so people were aware of what they are. And we'll keep defining them because that's how you learn stuff. But we wanted to start out with this. So first of the terms is propellant. So the propellant is the oxidizer and the fuel, which are what chemically react and create the chemical energy. So this is the material that gets accelerated out of the nozzle and it creates a thrust. So like in hybrids, for example, the oxidizer is the liquid and the fuel is the solid fuel grain. The other term we use a lot is the oxidizer fuel ratio, OF ratio, which is pretty simple. It's literally just the ratio of, specifically by mass, of the oxidizer to the mass of the fuel. Different combinations of the types of propellants you use and also the engine conditions will create different optimal OF ratios. And of course, you're always trying to get an optimal performance. So you want to go with the optimal OF ratio. So mass flow rate, this is how much mass moves per second. So it's a variable and its units are kilograms per second. You can kind of think of it as velocity, but it's different. So it's not like how much distance it moves per second, but it's like over a singular space, how much mass is moving through that space every second. So it's used a lot when you're talking about fluid flow characteristics and conditions. So it's something we keep track of, especially for the liquid oxidizer. ISP, or specific impulse, it represents the change in momentum per unit mass. So what that basically means is it's basically like efficiency. So it's like gas mileage in the car. Why it's important is that you want the higher your specific impulses, that means you can carry less propellant to get the same thrust. So if you have less propellant, you have less mass. Anything in aerospace, less mass is good because there's less gravity affecting it. And also vapor pressure. So vapor pressure is the pressure exerted by a vapor, a gas, and it's when it's in thermodynamic equilibrium with its condensed phase, which in our case would be a liquid. So this is the pressure that it pushes the oxidizer through the system. This one is probably more vague than the other ones, I would think, but we're going to get deeper into it in the presentation. So let's get back to it. But we'll keep reviewing these things. Every time we get to something, we'll define it, but we figure there are going to be a lot of things like this throughout. So now Raj is going to start talking to us about oxidizers.
So hey y'all, my name's Raj. So today I'm going to be explaining what essentially an oxidizer is. So if you guys remember by any chance the layout of our engine, there's like a huge tank at the top and we call that the oxidizer tank. Essentially it holds something we call nitrox. So nitrox in our engine is essentially an oxidizer. But to understand what that actually means, we need to understand what an oxidizer is. So for this part of the presentation, I want you to keep three chem terms in mind. We need to understand what a redox reaction is, or like a reduction oxidation reaction, vapor pressure, and a mixture. That's the word I was remembering. So we need to remember, so essentially an oxidizer is a component of a chemical reaction called a redox reaction. A redox reaction is essentially like two substances reacting where one substance donates an electron to another substance. So in this case, the substance that accepts the electron is called the oxidizer. In our engine, we have nitrox and paraffin wax. So when the nitrox and paraffin wax is burning inside the combustion chamber, essentially what's going on is that there is a chemical reaction going on where one electron goes from the goes from the paraffin to the nitrous oxide. And in doing so, it essentially like loses, like it goes from a higher energy state to a lower energy state. So there's like a loss of energy somewhere, but you know that we can't create or destroy energy, so it has to go somewhere. And that energy being expelled is in the form of heat. So like you can see here, it's just like some stuff burning, but that is essentially what we call a redox reaction. So could you go to the next slide, Larky? Thanks. So in our case, we're using something called Nitrox 96. So nitrox in and of itself is like a mixture. It's essentially nitrous oxide and oxygen. So you know how like Diet Coke or Coca-Cola is like a mixture of water and carbon dioxide? Soda is a mixture of water and carbon dioxide. In this case, imagine like nitrous oxide is the water and oxygen is the carbon dioxide. It's like bubbled through. So what we do is that we take nitrous oxide and we bubble through gaseous oxygen, and then it dissolves into the nitrous oxide. And that is nitrox. Now it's specifically nitrox 96 because when we like during manufacturing, we set the properties such that there is 96% of nitrous oxide by mass. So we call it nitrox 96. So there are like 3 specific reasons we do that. One is that it's safer. So it's safer because of something called minimum ignition energy. So minimum ignition energy is kind of a complicated topic, which if you guys have questions later on, you can ask me later. But the gist of it is that when you have a substance, sometimes if you heat up that substance enough, it will decompose or break down into like two separate other substances, which can then react with each other and then on its own create heat. So instead of it reacting with paraffin oxide, it can just react with itself. And we don't want that, because essentially what we're trying to do is that we're trying to take the stored energy between those two substances and then create heat when we want it. But if we let it react with itself, it's just going to decompose inside the oxidizer tank and it's going to essentially explode. We don't want that. So we use nitrox because through some cool stuff, what happens is that the minimum ignition energy of that nitrox increases. And that's great for us because stuff becomes safer. 2, it gives us better performance. That is because when you mix oxygen into nitrous oxide, its oxidizing capability goes up, which means that it is more likely to accept an electron from something that can give an electron, like paraffin wax. So since oxygen in and of itself has higher oxidizing capability than nitrous oxide, it essentially becomes better at doing its job. So it gives us like a slight performance boost. It's not that big a deal because we only have like 4% oxygen in the liquid phase. So it's not a great performance boost, but it is there that it's interesting enough for us to talk about, which we did talk about in our paper, if you guys want to look it up. 3rd thing is simpler engine design. So this is where I wanted to talk about vapor pressure. So Larky talked about vapor pressure, which is essentially the pressure that a gas will exert on its surroundings. So if you imagine like you have a closed cylinder of fluid, like it's completely sealed off, and there's just like a little bit of fluid and a little bit of vacuum. So what's going to happen is that fluid's going to boil off and then create a vapor. And there's a specific pressure at which that vapor stops evaporate, like the fluid stops evaporating, and that's when it reaches equilibrium. There's a specific pressure for each separate liquid, and for our engine, using nitrox has a higher vapor pressure at lower temperatures compared to nitrous oxide. So it's great for us because then we get to use a higher vapor pressure, which helps us push the oxidizer from the ox tank down into the combustion chamber, which is essentially how like we feed oxidizer from the ox tank to the combustion chamber. Are there any questions about how oxidizer works? Is there anything that you guys didn't understand?
Yeah, I have a question.
Yeah.
I don't know about like liquid versus solid rockets. So I know a liquid engine needs oxidizer. Does a solid motor need oxidizer? Is that like mixed in or?
Yeah, it is. That's a great question. So in solid motors, essentially what happens is that you have two solids. One solid can, like, solids can also be oxidizers. Like potassium nitrate, I think, is a good oxidizer, if I remember correctly. And potassium nitrate is also a solid. So if you take like what do you call it? Let's say you just take like wax and put potassium nitrate and then mix it together. There's a good chance that it's going to explode because wax is a fuel and potassium nitrate is an oxidizer. But both of those things are solids. So theoretically, yeah, that a solid does have an oxidizer in it.
And so what causes that not to just oxidize the wax and start exploding the minute you mix them together?
So in a solid motor, like, they choose the oxidizer and the fuel very carefully to make sure, and then it's put in another medium, which I think separates it. But then when you put just like a little bit of energy, like a spark, that'll kind of like melt the medium, and then it'll create like a chain reaction where it'll start burning the entire thing.
Okay. Got it.
Does that make sense? Does anybody
Yeah.
have a better answer, like, guys?
Yeah, I'll speak a little bit more on this in day 3 when we talk about ignition. But unless you're dealing with hypergolic fuels, which will ignite spontaneously when they come into contact, most fuel and oxidizer combinations require a high energy threshold that they have to cross in order to start reacting and trigger the chain reaction of combustion. So solid fuels are typically pretty safe when they're stored until you give it a spark or a pyrotechnic ignition. So that's the reason they don't just spontaneously combust when they're mixed. Does that make sense?
Also, yeah, that's like a good point where there's something called, when I talked about minimum ignition energy. So minimum ignition energy can also, so I define minimum ignition energy in terms of like something reacting with itself, but essentially you do have minimum ignition energies between two different kinds of substances. So if you've got potassium nitrate and wax, both of those things can combust and react in a redox reaction, but you do need to provide like an initial amount of energy to get that reaction going. All right. Anything else? Or if there are no more questions, I will hand off to the next slide.
Cool, thank you. Oh, never mind. I'm ahead of myself.
See, okay, so basically to simplify everything that Raj talked about in one sentence is that using your propellant, choosing the propellant is one of the key factors in rocketry. And to do that, we have to have like the right mixture of oxidizer and fuel, and CEA does that for us. Basically, it's a online tool created by NASA which solves a bunch of thermochemical equilibrium reaction equations as well as properties for complex mixtures. So the rocket problem specifically focuses on like solving for engine performance parameters such as ISP and other specific heat ratios that are involved during the whole process of combustion itself. It's very easy to use, and the only thing that we need to know is the chamber pressure and the exit pressure. So the exit pressure is usually just the atmospheric pressure. So or in vacuum it differs because then it's a different pressure itself. But yeah, so the only thing you need to know is how much pressure is your combustion chamber gonna be under during the reaction. So for our purposes, the chamber pressure was 30 bars. And over here you can see the graph showing the different oxidizer and fuel mixes that we have, that we kind of analyzed before choosing the specific Nitrox 96 paraffin combination of propellant. And here you can see like how the ISP correlates with the OF ratio, like how it's changing with the OF ratio. So to have the most efficient engine, we need to have the highest ISP, and that is yielded at an OF ratio of around 4 for our Nitrox 96 based fuels. So oxidizer. So that is why we chose Nitrox 96, and you can see like the slight increase in performance it gives that Raj was previously talking about.
Yeah, this
Just
is pretty cool because you can find this online. So we can send the link
Yeah,
out
I
after
can put
this.
the
if you
link
want.
right here in the chat.
Yeah, if someone wants to put in the chat.
I had a quick question.
Yeah.
So, correct me if I'm wrong, but isn't oxygen the best oxidizer? So is it just, are we not using LOX because it's hard to keep as a liquid because it's like you have to keep it really cold?
Right. Yeah.
Okay.
LOX is the best oxidizer. That's why like most liquid propellant rockets, like the really big ones, use LOX and liquid hydrogen as propellant choices. But it's definitely way more difficult to work with, and like it's also very difficult to store. So like those are the challenges that it has, and yeah.
Yeah, I think for propellants, the difficulty with storing them is actually a huge issue that you need to take into account. Sometimes just as much as the performance. Cool. You guys are asking pretty good questions today.
I also wanted to point out that it's not actually true that LOX is the best oxidizing agent. It's like the best thing that we can use, but technically elemental fluorine is the best oxidizing agent. So if you guys do want to look up like the chemistry behind this, just like Google oxidizing and reducing agents and just like read through something on Wikipedia, and like you'll get a pretty good understanding of like how that works.
It really depends upon what like your mission objectives are in terms of choosing your propellant. So for us, like because we're gonna be launching this rocket in New Mexico, maintaining a constant pressure and temperature was very important because it gets really hot there. So that's why earlier we were just gonna do nitrous oxide, but then like that's why we chose Nitrox 96 because it's much safer than just nitrous. Any other questions regarding CEA? All right, next slide.
Hello, hello. I'm Ira, and I'll be talking about the Oxidizer Tank. Okay, so that is a diagram of, an example of a diagram of a hybrid engine, and the Oxidizer Tank is at the very top. The purpose of it, well, is just to hold the oxidizer. And here's a rundown of the basic specs. The body of it is going to be composed of thin-walled aluminum 6061 T6 at an 1/8 inch thickness. The design pressure of it is going to be at 76 bar with a minimum safety factor of 1.5. And the storage pressure is going to be 45 bar at 0 degrees C. So I'll be talking more about these two pressures on the next slide. So don't worry if it just seems arbitrary right now. This is just a basic rundown. Basic specs continued. It's going to have rubber or fiberglass insulation, and it's going to hold 8.4 liters of nitrox. It's also going to have a venting solenoid valve, a pressure relief valve, and a pressure transducer. Some of the specs that are yet to be determined is the end cap type, and whether we want a permanent welded design or a removable bolted design. Another thing that we're still hashing out is the filling and dumping system. Okay, here is a example diagram of where all the parts are going to be located on our ox tank. So there's a couple more animations, Andrew, if you want to just click through.
Should I just?
So that's okay. Yeah, just click through all of them. So yeah. Okay. So yeah, these are just the pressure relief valve hole, the venting solenoid hole for the pressure transducer, the end caps, and the oxidizer body.
Could you explain what the pressure transducer does?
It measures pressure from within the oxidizer tank.
Okay, noted.
Yeah. Yeah, and most of these will be explained in the next 2 slides. That's where the meat of this presentation is. Okay. Sorry. No, it's all right. You're all good. I shouldn't have added these transitions. I forgot it was going to be another person clicking through. Okay, so as I mentioned before, none of the values that I mentioned were arbitrary. There are reasons why we picked what we picked. So starting with the aluminum body, why is it 1/8 inch and why is it aluminum 6061T6? Aluminum 6061T6 is just an alloy of aluminum. The reason why it's 1/8 inch is because 1/8 inch meets our pressure requirements. And the reason why we chose that type of aluminum alloy is because it has high oxidation resistance with a high strength to weight ratio. And it's also like highly commercially available and very, very easy to machine. So it's lightweight, low cost, oxidation resistant, and meets our requirements. That's all we want. And why do we need insulation? That's because we want to keep our oxidizer cool at 0 degrees Celsius. For safety reasons, to keep the vapor pressure of nitrox lower than 45 bar. And also for performance reasons, because as you increase the temperature, the amount of dissolved O2 is lowered. So we want to keep the dissolved O2 high and the vapor pressure low. So why is the storage pressure 45 bar at 0 degrees C? 0 degrees Celsius, because it's a very, at that point, it's very, very easy to cool with a really simple system, right? Like the most simple system would be an ice bath. So it's we don't have to deal with any other type of exotic cooling system. We just dunk it in an ice bath and we're good. Why 45 bar as opposed to something higher, so like 80 bar? The lower pressure actually allow us to manufacture thinner tanks, which saves on mass cost a lot. And 45 bar, but 45 bar isn't too low such that the dissolved O2 content is too low. So we're still getting most of the safety and performance benefits. So why exactly is the design? Oh, there's a question. What is mass cost? So that's basically how much mass, like our entire system, is going to weigh. And it's we say that it's a cost because we want to basically reduce it. Like this is a design parameter that we want to optimize because lower mass, higher altitude. Okay, thank you. So why is how did you decide on the 45 bar number? So as I mentioned, oh, okay. So in order to manufacture nitrox, you have to set some sort of upstream pressure. So in order to manufacture nitrox, you have to have your container of liquid nitrous, and you have to have your container of gaseous oxygen, right? As Raj mentioned before, nitrox is a mixture of nitrous oxide and oxygen. So you're going to have your higher pressure gaseous oxygen and your tank of liquid nitrous oxide. And you're going to set an upstream pressure such that the oxygen flows into the nitrous oxide tank, right? And it just so happens that at 0 degrees Celsius, the equilibrium pressure is at 45 bar. So the 45 bar is in consequence of the 0 degrees Celsius cooling point. So I hope that answers your question adequately. Okay, so why is the design pressure higher than our storage pressure of 45 bar? That's because even though our storage pressure is 45 bar, we want to design our tank for the worst case scenario. And it just so happens that nitrox, the vapor pressure of nitrox goes up to 73 to 76 bar at 36 to 40 degrees Celsius. So if our cooling system were to fail, we would want the structural integrity of our tank to be maintained still. Cool. Next slide. Actually, are there any questions? Do we have to load the nitrox really soon before launching? Then so it doesn't heat up. So we plan to, so there's going to be a ground tank where we're going to keep our nitrox before we actually fill it into the oxidizer tank. And that's going to be submerged in the ice bath. And then before launch, we'll pump that into the oxidizer tank. And that's where the insulation comes in. But the thing is, we don't know how long it's going to be on the test stand. Not the test stand, the launch pad before it goes up. So to answer your question, yes, we do. Hopefully, we do load the nitrox really soon before launch. Does that lead to why the chamber pressure of 30 bar is less than the 45 bar vapor pressure of the nitrox? Can someone working on injector answer that really quickly in chat?
Yeah,
Pressure
so
drops.
we're going to get to this on Monday, which is day 3. But at basically between the oxidizer tank and the combustion chamber with the fuel grain, there's a whole feed system, and there's a piece called the injector, which is the last piece that it injects the oxidizer into the combustion chamber in a way that the two can react the most efficiently. But to get the liquid oxidizer to accelerate through the system, you need to have a pressure drop. So a pressure drop is just a difference. So Nick, you mentioned that so 45 bars are upstream. Upstream is further up the system, the oxidizer tank, 45, and downstream it's 30 bar. So it's going to move from high to low pressure. So we'll get much deeper into that, but that's basically it. So the keeping track of pressure drops is a very big part of rocket engine calculations.
Awesome, thank you.
Yes.
Cool, I think we're ready. Oh,
okay.
To go to the next slide, yes. Okay, so safety is going to be a very, very important part of designing the oxidizer tank because it is a pressure vessel that's holding some high pressure liquids. So in order to monitor and protect the oxidizer tank and ourselves against pressure buildup, there's going to be a venting solenoid valve at the top of the oxidizer tank. So that basically, when we're in the filling process, we open that valve slightly so that it can vent the ullage space of excess pressure. And once we're done with the filling process, we close that valve. There's also a pressure transducer. That's where we're going to get our pressure readings and know when everything is okay and when to stop filling. So what is the point of the pressure relief valve if we already have a venting solenoid valve? So the venting solenoid valve is actually going to be controlled by avionics, right? That's the electronics. That's basically the engine electronics, and it may fail. We can't ensure that it works 100% of the time. So the point of a pressure relief valve is to serve as a failsafe, because that doesn't require us to manually actuate it using electronics. It just pops open at a certain if the oxidizer tank goes up to a certain pressure. So that's essentially a backup plan in case the solenoid valve fails. The next thing is a safety factor. What is it, why we need it, and why a safety factor of at least 1.5. So a safety factor is basically a multiplicative coefficient that we apply to our design pressures. And that basically tells us how far past the design point the pressure vessel will actually fail, right? It's basically a backup to the backup plan. So if our solenoid valve fails and our pressure relief valve fails, we still want to be able to have the tank not fail on us. So this is like a fail-safe to the fail-safe. And I think there is a, okay. I was just reading chat. And the reason why we have a safety factor of 1.5 is that we don't want to go too high, right? Because if we go to a safety factor of say 2, then we're eating into our mass cost, and it's going to be too much weight with no further benefits. There's a point of diminishing returns when it comes to safety factor for rocketry. So why exactly do we have 8.4 liters of nitrox? That seems rather arbitrary, but that's because we have a 4-to-1 oxidizer to fuel ratio, and that's actually decided based on the CEA data we received. And because of that, it's going to hold 6.9 kilograms of nitrox at 45 bar with a density of 880 kilograms per meter cubed. So that's why it takes up that much volume. Any questions at this point? I know people have been asking in chat. Okay, wait, if we only want the oxidizer at 45 bar and the relief valve keeps it at 45 bar, then why do we need the solenoid and transducer? So the relief valve actually doesn't keep it at 45 bar. The relief valve doesn't actuate at 45 bar. It actuates, we haven't picked a value yet, but it actually actuates somewhere above 45 bar, like 60 or 70 bar. But it's going to be over the storage pressure, but it's going to be under our maximum allowed operating pressure, if that makes sense. Okay.
Next slide.
Yeah, I think we're all good. Could you re-explain the safety factor? Okay, yeah. Oh, never mind. I think Justin has it. Okay, cool. Thank you.
Yeah, Justin's answer is perfect.
Okay, yeah. I think we can move on to the next slide. So, how exactly do we, perform the calculations to design, to dimension our oxidizer tank? Well, we basically designed our oxidizer tank per ASME specifications. So ASME, it's an acronym, and it stands for the American Society of Mechanical Engineers. And it basically develops standards and codes used to regulate many things in the mechanical engineering industry, from elevators to escalators to cranes to, conveniently, pressure vessels. So why exactly do we want to manufacture it per ASME standard? It's for two different reasons. For safety, because they've extensively tested these formulas in order to come up with them, and also to ensure the quality of our design. We don't want any failure. So ASME accounts for all of that pretty well. And very conveniently, as a section dedicated to pressure vessel design, and that's section 8 of the pressure vessel handbook. And it's actually separated into 3 different divisions, where the different divisions basically get stricter and stricter as you move up in design pressure. So ours happens to be below 3,000 psi. So it's going to be we're going to be manufacturing it per the section 8, division 1 ASME standard. Yeah. Good answers in chat.
Yeah, so just to touch on something we've been talking about in the chat, as a student organization, our safety is really our main concern almost all of the time. Obviously, we have performance goals, but those are always sacrificed for a bit of safety. And also, I think I've also gotten this question a bunch separately, is that most of the stuff we do is based on what's already been done. So we're not necessarily like a research group that are trying new things. So we like to do, in the vein of being safe, we like to do things that have worked so we can learn from that and replicate that. Yeah, that's different.
Cool.
Okay. Next slide, Myron.
Mm-hmm. Yep. Okay, so this would be an example of one of the formulas that we've borrowed from the ASME pressure vessel handbook. And this is how we used, this is what we used to calculate the actual thickness requirement of our tank body. So the left formula is a calculation of the required thickness given all of the other variables, while the right side formula is a calculation of the maximum pressure given all of the other variables, where P is the maximum operating pressure, the R is the inner radius of the tank body, S is the safety factor, E is the joint efficiency, and T is thickness of the body. And joint efficiency comes in when we start to do welded designs, because the material strength decreases at the seam. So we always want to calculate the strength the strength by using the weakest link of our vessel. Okay, I think we're ready for the next slide. In addition to the tank body, we also have these very nice formulas to calculate many different ASME standardized end caps. And in the interest of time, I'm probably not going to go in detail all of these, but if you come back to these slides later, you can have a look. I actually have a good summary slide on the next slide. So, okay. So the four main ones that we are considering is flat heads, hemispherical heads, elliptical heads, and flanged and dished heads. And this is just a summary of all of the pros and cons of each type of head. And I've actually put these in a table where one is if it has the most desirable trait in that category, and 4 if it has the least desirable trait in that category. Okay. Another thing that we are considering right now is welding versus bolting the end caps. So for a welded design, it's actually a very standard design, a very simple design, and it's also very easy to stress analyze because it's just one entire, one complete vessel. And because it's a standard design, it's also very easy to manufacture per ASME standard. We just pick end caps, pick a tank body, weld them, and that's basically it. And because it's a welded design without all the bells and whistles of flat end caps, it's also lower mass. So it saves on mass costs there. So for the flange and bolted design, it's actually not very common in oxidizer tanks. There's additional stress calculations needed to take into consideration the flange and bolts. And because it's a flange and bolted design, we don't want any leaks at the seam. So we also need to select O-rings. That's also a design consideration. So because of the flange and bolts, there's going to be more mass involved in the design. But even though it has all those cons, the two pros that it has is that it has a much more simple cleaning procedure. So if we want to clean our oxidizer tank of contaminants, this is actually a very, very easy to clean system because you just unbolt all of it and then clean all those parts separately versus a welded design where you only have a tiny orifice to clean through. And because it's a flange and bolted design, it's actually modular. So in case if we want to change up our design, we can just change parts of the system as we see fit. Versus a welded system, you already made the entire thing. So if you want to change one little thing, you have to go manufacture a whole different oxidizer tank. Does that make sense? Any questions? Really quick, when you flange and bolt the end cap versus welding the end cap, how do you calculate joint efficiency? Okay, so if you take a look at the bottom diagram on the right-hand side, that's an example of a flange and bolted design, and you basically take these flat discs, and you weld it to the tank body, right? So the joint efficiency at that weld will determine the thickness of the end caps. Does that make sense? How do you calculate joint efficiency? Oh, how do you calculate it? Okay, so that's also in the ASME pressure vessel handbook. They actually have like 30 different types of welds that they calculate a joint efficiency for. So it's they basically extensively test it, and they provide a coefficient that we multiply the material strength by to calculate its joint efficiency after welding. So yeah, the pressure vessel handbook is very useful for oxidizer tank design. So the end caps will be a different thickness than the main body of the oxidizer tank. Yes, it will be. It will most likely be. Well, if we want to match the safety factor, then yes. We can manufacture the oxidizer tank end caps to be different thicknesses, but then we just we have two different safety factors for the same component, and that's just it's either not safe enough or it's wasted mass. So that's why we want to match up the safety values, safety factors. Okay, the last slide. Here's just a quick summary of what to do, what we have left to do in order to manufacture the oxidizer tank. So the main focus will probably be choosing an end cap design. As I mentioned previously, if we want a permanent welded design or a removable bolted design. We also have to figure out, because we're designing new end caps, how we're going to integrate the pressure transducer, the relief valve, and the venting solenoid valve. And we'll also have to consider O-ring placement if we do end up going with bolted end caps. Then after all that is completed, we'll have to do a final stress analysis of the entire oxidizer tank using finite elemental analysis software. The next thing that we have to do is we have to find a new pressure relief valve spec'd for our new design point. So this isn't actually the first iteration of the oxidizer tank, which is why we have a pressure relief valve that's not within spec currently. The next thing we need to do is design insulation, basically a bunch of thermal analysis such that we figure out the rate at which heat is lost from our oxidizer tank at 0 degrees Celsius. And then we can optimize the thickness of our insulation accordingly. And after all that is done, this will culminate in a hydrostatic test where we basically pressurize our oxidizer tank with water at 2 times the operating pressure, and we let it sit to test for any leaks or failures. Question from Nahar. Okay. For insulation, we are choosing between fiberglass and rubber, right? Yes. And the thickness is variable depending on our tests. We don't. We want it thick enough such that the loss of heat is reasonable, but we don't want it too thick such that it again eats into our mass cost. Good questions. Okay, so 2 times the operating pressure, not the. So this is going to be 2 times the storage pressure, not the maximum allowed operating pressure. Does that make sense? So our storage pressure is 45 bar, and our operating pressure, maximum allowed operating pressure, is going to be 1.5 times the design pressure. So we're actually going to be pressurizing it to 90 bar. So in theory, it won't break. Yeah, so that goes back to the 2 different pressures that I talked about earlier. One is our storage pressure, one is our design pressure, right? And the maximum allowed operating pressure is 1.5 times the design pressure, which is 76 bar. But our storage pressure is 45 bar because nitrox, the vapor pressure of nitrox reaches equilibrium at 0 degrees Celsius at 45 bar, if that makes sense. So yeah, two different pressures that we're considering. The pressure that we're going to store the nitrox at, and the pressure that we design our tank around. Yes, safety factor is based on the 76 bar, not the 45 bar precisely. Yeah, good questions. So we are designing our tank to withstand 1.5 times the 76 bar pressure. Yes. So 76 times 1.5 will be our maximum allowed operating pressure. But we're not gonna, like during hydrostatic testing, we're not gonna push it to the limit because we don't want our oxidizer tank to fail on us. So 2 times the storage pressure of nitrox is enough for verification purposes.
Cool. All right. Great questions, guys. But thank you, Myron.
Absolutely.
Very good. Very good review. Okay, we're going to start doing the feed system. Savara's not feeling well right now, so I'm going to take over. But we started late, but we're kind of approaching an hour. But I promise this is the last section of the day, and we'll take some questions at the end for anyone who has more questions, because we want to make sure you guys are digesting all of this, because we know it's a lot. Anyway, So the feed system, so here's what our feed system, our whole engine looks like. Our feed system is the bulk of the piping, the valves, and it's what connects the oxidizer tank to the combustion chamber. So in the fuel and the oxidizer are separated, and the feed system is what links both of them together. So its main purposes are to transport the oxidizer in a safe and controlled manner into the combustion chamber. So when we say safe, we mean that we have multiple what's called fail-safes and protections. So those are in place primarily for the safety of like us, the members of the team, but also we don't want to damage the equipment and the things that we've built because those are also valuable. And as if we haven't stressed this enough, but rocketry is inherently like very dangerous. So the biggest and most important thing we have to consider when doing any sort of design work is taking care of those safety concerns and just making sure you're aware of everything going on. And it also, so when we say controlled, we mean that we need to be able to physically stop and start the flow of the oxidizer to begin the combustion process. So a couple other like smaller purposes that we use the feed system for is to provide us thermodynamic data. So we have more pressure transducers so we can get data of the pressures at different points along the flow, which will give us the ability to understand what's happening in the feed system, both for performance and also for safety, because if the pressure gets too high, we want to end and abort the test. Any questions? I guess feel free to just keep putting them in the chat. That's been working pretty well. So I'm just going to go over a bit of the requirements for the feed system and how our design fits into and around those requirements. So due to the pressures in our system, which reach 1350 psi, we need to make sure our lines, which our feed lines, which basically like the plumbing and piping, are resistant to these high pressures. And also our oxidizer is stored at 0 degrees Celsius. And we need to make sure that the materials in our feed system do not weaken at those freezing temperatures. So there's a quick way. I'm going to finish this. I'll get to that question at the end. So also, given that Nitrox is an oxidizer, we also want to make sure that there aren't any leaks in the system, because if there's a leak and the oxidizer gets out somehow, we don't want to have any sparks or ignitions that could cause any damaging events. We also want to make our system as easy to assemble and disassemble as possible so that we can break it down and put it back up again. When you're designing hardware parts, there are two very important things to keep in mind, which are designed for manufacturing and designed for assembly. So Myron has kind of talked a lot about like design for manufacturing thing with all the different end caps we're considering. Because you can design something that could be a perfect engineering device, but if it's something that can't be made, then it doesn't matter if you can't make it. So that sort of thing. Yeah, and then finally, we also want to make sure that we trust all the devices like that are part of the feed system. So to take care of those requirements, we have a couple parts of our designs that handle that sort of thing. So one is the material choice. We use 316 stainless steel, which similar to aluminum 6061, 316 stainless steel is just a specific alloy, which is common and easy to obtain as students and easy to machine and stuff like that. But one of the reasons we're using it is because it's really strong and can withstand all the high pressures and maintain its strength at low temperatures. We're also using compression fittings, often called Swage Lock, which is the most popular brand that uses them. And these, there's a picture on the slide right here of what a compression fitting looks like. So between every device in your feed system, every like part of the plumbing, you need a fitting, and a fitting is just really a connector. So you want to make sure that those connectors don't leak. That's a very big deal, and that they're also easy to assemble because we're going to be like putting them on like with our hands and tightening them with wrenches and stuff like that. We're also by parts, like we don't make this compression fitting. Like theoretically, this fitting was machined by some company, Swage-Lock, I guess. So technically we could manufacture it ourselves, but that would be super hard. So we let professionals take care of that. So there's a shop online called McMaster Car, and they have tons and tons of all sorts of different pieces of hardware that you can buy for any sorts of projects, whether it's like rockets or cars or anything. McMaster Car is a great place to go for that sort of thing. So they're very professional, very trusted. So all their parts are trusted. So I know there's been a bunch of questions in the chat. It looks like some good discussion. Yeah, so someone was mentioning, yeah, it looks like everyone is handling all these questions pretty well. But basically the questions were about the injector, which is, we're going to talk a lot about it next time. But it's kind of part of the feed system. It's kind of part of the combustion chamber. It's technically like the singular piece that connects the two. But yeah, look at the chat. There's some cool stuff going on there. So in our feed system, besides the feed lines and the connectors and compression fittings that we've mentioned, there are 4 kind of important devices that you'll find in our feed system. So these are a main ball valve, a check valve, a solenoid valve, and a pressure transducers. So the main ball valve, which is actually in the picture on the slide here, it is it's servo actuated, and when we say servo, that means like a servo motor, which is just a type of small electric motor, which are actually the 2 red things. So the valve itself, I have my mouse here. The valve itself is this piece here. So this is a ball valve, and it has, you can kind of see it. It's closed right now, but there's a ball in there, and there's a hole. So then when the top section turns and rotates, it'll rotate the ball, and then the ball will have a hole. When the hole lines up with the feed line, the propellant will move through it. So our main ball valve has 2 servos, which is these 2 red things, and it has a gear system. So as the servos move, they connect to the by gears, they connect to the valve, and that's how we rotate it. So as I said, it controls the flow of the oxidizer, and it is a crucial piece for the engine operation and safety. And it's called the main ball valve because it is the main valve. It's what keeps all the oxidizer in the oxidizer tank until we want it in the combustion chamber. So it's very important there. It's also one of the pieces that we're going to be testing pretty soon because we've built it and we've never put it under any sort of pressure. So we're going to hook it up to some inert nitrogen, which means it's safe, even though it's at high pressure, but the nitrogen is pretty safe to use. So that's how we're going to see like how it holds up under high pressures. See, there's a question about whether you have the 2 servos for redundancy or does it need both to provide enough force. Off the top of my head, I actually can't remember, but I'm pretty sure it needs both to move the valve itself. The valve is a decently heavy piece of machinery, so we can double check on that though. We have all of our notes, but off the top of my head, that's what I think. Second thing you'll find in there is a check valve. So this is, again, more of a safety thing than an actual control valve like the main ball valve is. So the check valve is a valve that only allows the flow to go in one direction. So that means it allows the flow to go from the ox tank to the combustion chamber, but what it prevents is that any gases from the combustion chamber can't move back through it. And it's important because you don't want anything to be going back up into the oxidizer tank. It should all be moving down. So check valves are super important for safety. Third thing is a solenoid valve. So we've mentioned the solenoid valve because we used it with the oxidizer tank. But what it does is it slowly leaks the liquid, and so it's kind of like the backup safety thing. So if we ever have to abort, if you ever have to abort the test, or like you're trying to fill, more likely would be like when you're trying to fill it and like something happens, like, oh no, we can't test right now or something. We need to end this. But also then you'll have the propellant in the system, and you don't want it in the system. You can't just pick it up and move it when there's propellant in there. So this is something that we would use to vent the system, allow the propellant to exit. And the fourth thing, so this one's not a valve, and we've mentioned this a lot before today, are pressure transducers. And these are just pressure sensors. You hook them up in the way they work is they actually give an electrical like voltage signal to whatever your controlling device is, whether it's a computer or like a microcontroller, like a teensy. And that voltage is converted into pressure. So based on the fluctuation of the voltage, you'll get a fluctuation of the pressure. So they give us real-time pressure data. They allow us to understand what's happening in the feed system, and also, so both for performance and also for safety. That's also something that we're going to be doing pretty soon, because we need to calibrate them. So like I said, how it gives you a voltage and that gets converted to a pressure. So calibrating them is setting up so that it understands what voltage is exactly what pressure. Someone was asking in the chat about whether the servos, like how quickly the servos move the ball valve. And as Raj is now explaining in the chat, it actually moves pretty quick. So that there's a video, I guess a GIF that's on our wiki that I think was linked in the chat. So it moves pretty quick. It's pretty cool. And then so here's what's left to do in our feed system. So we have almost all of the components in our feed system, but they're all in a room right now. They need to be assembled. We've mentioned this a bunch, but we're going to be testing that main ball valve and calibrating pressure transducers. We need to dimension everything and make a mass estimate. So what that means is we have all these components that are being attached together, and they need piping between them. So we also need to determine the length of that whole section. Ideally, it's as small as possible, but it will take up some space. Like we said, especially anything in the air is going to be fighting gravity. Force of gravity is mg, m is the mass. So mass is super important. You need to understand your mass. Second is the flow rate estimate. So flow rate was one of those vocab words from the beginning, which is defined as kilograms per second. So mass of the it's the mass of the oxidizer that moves through at every second. So that's super important to the injector, which is what inserts the oxidizer into the combustion chamber. So that flow rate will help determine what happens in your combustion. So a lot of those pieces, all the valves and transducers, they're all controlled electronically, right? In like an engine or a rocket, all the electronics would mostly be under avionics, kind of the brain of the system. So the IREC avionics team is helping us out a lot with our avionics system right now. So they're doing a lot of this. And last, we need to figure out the cleaning procedures, because every time we test, we need to clean, and that's a big deal. Okay, so that is day 2 of Crash Course Propulsion. And we made it, we started 10 minutes late. We made it in 59 minutes. Incredible. But yeah, if you guys have you guys have had a lot of great questions, which have been awesome, because that really drives how we understand how we're talking about this. Thanks, Justin. But yeah, your questions are great.
I have a quick question.
Yeah.
I missed the first session, so if you explained kind of how the hybrid engine works, I didn't quite get that. But I was just wondering, what makes it a hybrid engine? Is it a hybrid between liquid and solid? Or?
You nailed it. Yeah, you'd be surprised at how many people not involved in rocketry think it's like related to hybrid cars. Yeah, so this is a slide from the first week. Also, our We're recording this, and we also recorded the last one, and we've put links in Slack and Discord about where to find the video from the last one. So if you want to watch that, it's up there. We're actually still, we're going to share this whole slide deck with everyone once we're done. We need to finish up a bit for the very last day, which is just the next week. So next week we'll share this with everyone. But it's just one slide that has like everything in it. No, that's not what I want. To go back to your question, yeah. So these are, especially commercially, these are the main two types. The main two types of rockets. So they're often liquids and solids, and they both have very particular uses where they're both in some situations they're better to use, in some situations like a solid is better, some a liquid. Like the space shuttle and a lot of other rockets have a combination of both. So that, I don't want to make it even more confusing. They have a combination, but it's not, the engines aren't combined. It'll be like they'll have a solid and a liquid. What a hybrid has is one liquid and one solid.
Yeah. What confused me about that is just I didn't see. Is there a like fuel tank somewhere? I see there's a grain and an oxidizer tank.
So when we say that the fuel grain is solid, what we mean, I think we have. So we're going to actually jump into fuel grain stuff next week, or I think next week, or sorry, well, definitely next week, but I think it's on Monday. Not to share all your slides, Ashish, but here's a quick preview. So this is what a fuel grain would look like. So it's wax, and it just has a hole in it. So the hole, the liquid oxidizer flows through that hole, and as the surface of the fuel grain hits the oxidizer, that's like the actual combustion.
Okay.
So when we say solid, that's what we're talking about.
So is the liquid fuel tank just not pictured in the diagram, or is it?
So, so we have a liquid oxidizer tank, and we have a solid fuel grain. So there are two propellants. One is an oxidizer, one is a fuel, which are the two things that make up combustion.
So then the grain is only the fuel. There's no oxidizer mixed in, so you can actually fully control.
Correct.
Oh, that's sick.
Yes, that's actually one of the big things about solids, is that in a solid engine, like a pure solid, they combine the oxygen and the fuel together, right? So once you ignite it, then it starts to burn, and it's really good because that's super simple, but you can't stop it. So that's why you see, like, whenever they're on like big rockets, they burn and then they just drop in the ocean. When you have liquids, you can actually, using the valves and stuff like that, you can actually control the flow. And what that means, like, that's basically like, that's essential to how SpaceX is able to launch and land their rocket. So they use liquid engines. So what they do is when they start, they turn the engine on, they go to space, drop off like their payload or whatever, right? But because they have valves that can close the flow, like right before the tanks are empty, they can hang on a bit, and then when they come back to Earth, they can turn the engines on again, and that's what slows them down. So that's something you can't do with a solid fuel with a solid rocket engine.
With a hybrid engine.
So technically you could do it with a hybrid engine. We're not going to be doing that because that's super hard to do, and that would just be really advanced, and it's really not something that's necessary for the competition and flight that we're trying to do. But that's one of the really cool things about hybrid, is that it exposes you to all the components that are being used in all different types of rocketry.
Nice.
So a lot of the reasons so a hybrid is really like a pure balance of both. It's more complex than a solid, but less complex than a liquid. It's kind of in the middle, money-wise, in the middle, performance-wise, and it's also pretty safe. So that's why we're doing it, because it exposes us to some of these higher-level things, but not enough that need to be like a full private company.
Right. Cool. That makes a lot of sense. Thank you. Sorry for not.
No worries. It's always good to review this stuff.
I gotta go, but thank you so much. That was really, really interesting.
Yeah, no, thanks for all your questions. Okay, so Liam, you're asking about Moves the injector, goes to the fuel grain. Yeah, so Liam, you're exactly correct there. So I'm going to pull up. So we're going to actually talk about like what this means later. But this is what's called a P&ID, which is that stands for Piping and Instrumentation Diagram. It shows kind of all the components of the system. So here, so maybe you can see this a little bit better now. So you have your flight oxidizer tank at the top, and then you have a couple of your valves. Like here's that solenoid valve I talked about, the main ball valve, the check valve, and the pressure transducer. So at the end of the feed system, it hits the injector, which is also the top of the combustion chamber. And then it injects it into the combustion chamber, which is where the fuel grain sits. So William, did that answer your question? Because you basically nailed it, but. Because a lot of people have asked about injectors. Just give you a quick preview. So this is what the inside of the combustion chamber looks like. So this yellow part here, this is a picture of our CAD. This yellow part here is our fuel grain, and the injector sits right here. So this is what an injector looks like. So the feed system would be sitting here, and it feeds into the injector, and it goes through, and it will atomize. Yeah, a lot of injector interest. That's cool. Injectors are very awesome. Yeah, Liam. So you asked what a ball valve is. So it's quite literally just a rotating sphere with a hole in it. Actually, I'll show. So this is our wiki, which I know we've talked about probably 100 times, and we've probably sent links out there. But I'll show you that GIF of
And feed system.
Yeah, thank you. Is it on this page or is it? Ah, here we go. Yeah, so you guys can see this. See how quickly it turns and. So Raj, this is your baby. If you want to talk more about it.
It is. So Nick, our grad student, he had gone back to France and he's back now. Wait for Nick. So Nick and another person who used to work on this project, Alex, designed this like a couple of years ago. But essentially my job was trying to put it together and get it to work. Essentially what we have is like we have this one plate that we machined, and then we bought just a bunch of gears, and we machined this little adapter piece that sits on top of the ball valve. So if you guys know what a ball valve kind of looks like, essentially it's like a tube with like just like a little handle on top. I don't know, like if that makes sense. So if it's just a tube and a handle on top, there's like this little rectangular piece on top which you turn to turn the ball valve. So we just put the gear on top, and then we attach the two servos next to it. It's not that complicated. If you guys go through the wiki, it should like it'll very. I've given like a really nice description of like how it's put together, so you guys can look at that some more.
Yeah, I'm gonna show that because that's super cool. So Raj made an entire assembly instruction. So here are all the components, and here's his recipe with detailed pictures of how to put it together. So this is one of the reasons we really love our wiki. We've put a lot of work into it, but it also has like really important information like this that wouldn't necessarily fit well in like another medium. So all the things we've talked about during our during the sessions, like they all have like their own sections. Well, we need to fill this out more, but you can actually see our initial meeting from May where we were starting to brainstorm some of the initial designs for the Ox tank. So this is a design that we're not going to be using anymore, but you can kind of keep track of like this stuff. So we like to keep track of most of our meetings, at least this ones that have like important information. With other really cool stuff in here. Some slides. Yeah. there's a whole bunch of information on injectors that I'll talk about them Monday. So. Yeah, so if no one has any questions, I mean, we're here to answer questions, but next session is Monday at 8. So. All right.
See y'all later.
Yeah. Thanks for coming, guys. Okay, I'm going to end my recording now.
Good job, guys.